Hey guys, Math 148, section 14.4, last section, maximum, minimum, and saddles. I should say maxima, minima, and saddles. What are saddles? Well, we'll get to that in a minute. So here's an example of the problems in this section. Question number 5 gives this function z equals x squared minus y squared plus 4x minus 6y plus 11. And it says find the relative maxima and minima. Okay, that's such a simple question. This is an example of a type of problem where the question is very clean, but the answer is very complicated. So don't let the simplicity of this question make you think that it's not multi-staged. So the way you want to answer these questions is you want to follow this test. There's a little box that gives a procedural test thing, and it's on page 896. So you have this function. The first thing we're going to do is find the derivative in terms of x and y, and to find this point a, b. So I will walk you through it. I don't expect you to know how to do this before I start the video. Here's question number 5 on section 14.4. Again, here is our z is equal to x squared minus y squared plus 4x minus 6y plus 11. And the first thing we're going to do is we're going to find zx, the derivative in terms of x. And another way you can think of that is you could think of it as the derivative z in terms of x, dz dx. So if you want, you can circle this. There's an x, right? So this derivative is going to be 2x, that's this piece, minus 0 plus, that's derivative y squared is constant, 4 times x, that's 4 times, derivative of x is 1, plus, that's a constant, 0, 11 is a constant, 0, so the derivative in terms of x is equal to 2x plus 4. Yay! Alright, you're thinking, that's great, why did I do that? Well, wait for it. Now we find the derivative in terms of y. I'm considering this step 1. Derivative in terms of x, derivative in terms of y. dz, or it's not really d, it's just this derivative thing, in terms of y, which is equal to, now I'm going to rewrite this function again so we can take the derivative in terms of y. Z equals x squared minus y squared plus 4x minus 6y plus 11. And we're taking the derivative in terms of y, so I'm circling the y's. Do you see why the circling is helpful? Otherwise it's very challenging to keep in mind what it is you're taking the derivative of. So the derivative of x squared is now 0 because that's a constant, minus the derivative of 2y squared is 2y plus x squared, or excuse me, 4x, that's a constant, 0, minus the derivative of 6y is 6 times 1 because y is the variable, and 11 constant 0, so the derivative in terms of y, or zy, the derivative of z in terms of y is negative 2y minus 6. Whew! That was step 1. But now, let's go back to our thing. We want to find where each of these, that's dz and dy, equals 0. We want to find this point AB where they're each equal to 0. This is, exactly like the other problems where we were trying to find the maximum minimum points of a function. So now we're just trying to do it on a three-dimensional surface. So I think of this as step 2. You set these equal to 0. So zx, which was equal to 2x plus 4, go back to the other page, you can see that, equals 0 at the point, well, this is going to be 2x equals negative 4. What you do to one side of the equation, you subtract 4 from each side, or x equals negative 2, right, that's where zx equals 0. The derivative in terms of x equals 0 at x equals 2. Alright, and what about z? Y. What is the derivative in terms of y? This was negative 2y minus 6 equals 0. When does this equal 0? Make that like that. Well, when we could bring the 2y onto that side and you get whatever. You figure this out. Spend a little time on this one if you need to, but you'll find out y equals negative 3. So you have zy equals 0 at y equals negative 3. All right, so this becomes the point that we will now be talking about. This is our A point, and this is our B point. So we have some point that we've found. It's technically, we're going to have the Z component too, but let's just work on this point so far. AB is going to be equal to the X component is -2, and the Y component is -3. And that's where the derivative in terms of X is equal to 0, and the Y place, the Y coordinate is where the derivative in terms of Y equals 0. So here's our point. We're going to focus on this for a moment. Okay, now keep going with this box. All right. Ah! Here's the next piece. We're going to find what the book calls D. There's just this number D. You can think of it as the difference. I don't know if they really say the demand surface. No, I don't know what the D is supposed to be called. They just call it D. The critical value D. I was trying to think of something clever. Derivative? I don't know. So it looks like this. You have the derivative of x, the second derivative of x squared of x, and second derivative of y minus the second derivative of x, first partial derivative of x, and then y squared. So you're probably going to want to write this down. And here's a simpler way, if you want to think of it this way. It's the second derivative in terms of x, second derivative in terms of y, minus the derivative, first derivative with respect to x minus times second derivative with respect to y squared. Okay, so we have to find 1, 2, 3 of these derivatives. Do you see that? zxx, zyy, zxy. Whew! Let's do those. Let's do it. We can do it. We can do it. Make sure I got my thing. Okay. So first we want to find zxx. Okay, well, the first derivative in terms of x, do you remember we said that was 2x plus 4? Remember that? That was the first derivative. The first derivative with respect to x. So if we're going to find the second derivative with respect to x, zxx, that is equal to, okay, 2, because the derivative of x is 1. Derivative of 4 is 0, because that's a constant. So that is simply equal to 2. zxx equals 2. Nice, we like that. What about zyy? Okay, well, that's going to be the second derivative in terms of y. The first derivative in terms of y, we just found that. So if you're keeping your paper tidy, you can find that it's minus 2y minus 6. Again, we're taking the second derivative in terms of y. So here is our variable, y. So the derivative of this piece is minus 2. That's the constant. Derivative of y is 1. 6 is a constant. That goes to 0. So this equals -2. So these pieces actually come together pretty quickly. So we have zyy, second derivative in terms of y equals -2. Second derivative in terms of x equals 2. Deep breath. Last one, zxy. Okay? So that's what we want to find. Remember, the derivative in terms of x was 2x, the first derivative, plus 4. Remember, it was right there, this one. First derivative in terms of x. First in terms of x. And now we want to take zxy. So we're going to do the same thing with respect to y. And you'll notice there's no y terms. Oh no, what happens now? That was supposed to be a sad face. So I would circle the y, but there's no y to circle. So we say, well, all right, 2x, that's fine. We don't have a problem with that. This is all a constant, so the derivative of that in terms of y is 0. 4 is a constant, 0. So that equals 0. So our last piece is zxy equals 0. Okay, now we're going to use that formula. You can take a moment there. I'm going to keep going. The nice thing about the video is, in theory, you guys could pause it if you need to. So, actually, let me do this. I'm just going to rewrite it. zxx is equal to 2. zyy, second derivative in terms of y is -2. zxy, first derivative in terms of x, second derivative in terms of y, 0. D, this number D, this difference that you're looking for, is going to be equal to zxx times zyy minus zxy squared. Why is that the case? Well, just go with it. For now, I don't need you to worry about the derivation of this thing. So d, zxx, that's 2, zyy, negative 2, minus zxy, 0 squared. That whole thing equals negative 4. So when you get down to this d, this big D as in delta, you're going to probably have a number. It's just a single number. 4. Negative 4. Okay, so D equals negative 4. So what? What does that tell us? Well, I don't expect you to know what that means. I expect you to have this written down, some version of this table written down on your card. You get 4 note cards on your final because one of them will probably have something complicated like this. Okay, so here's all the criteria. It seems pretty complicated, but now you just have your number. In this case, D equals negative 4, and you just kind of look and see what happens. Well, this part A says if D is greater than 0, then you have a relative minimum. Well, we're not in that situation. If D is greater than 0 and Z, the second derivative, is less than 0, well, then you have a relative maximum. If D is greater than 0, oops, this should be a less than. Less than. If D is less than 0, this is part C. Then there is, or if D is less than 0 at the point, I kind of rewrote it, AB, then we call this a saddle point because it is neither a relative maximum nor a relative minimum. And then you'll have this final one where it says if D equals 0, the test fails and you have to investigate the function. Now this is technically true, but for the purposes of this test, I'm not going to give you one like this because I want you to be able to, I don't want the test to fail. If I'm going to test you on the test, it should be an example where the test works. So you don't really need to worry about this one for the purposes of being tested in this class. So let's look at what this means. D less than 0, and remember that was our situation. D is negative 4. Then we have what is called a saddle point. What does that look like? Well, here's an example. A function, it's on page 898, example 2, z equals y squared minus x squared, and they go through all this and they get the critical point of 0, 0, 0, 0, and their d was equal to, their d was also negative 4. What? How likely is that? Maybe negative 4 is a common answer. I doubt it. But negative 4, so here's the graph, and that's why they call it a saddle point. I made a saddle here, so for those of you that have never seen a horse, you can picture what this saddle looks like. So the point is, right there, 0, 0 is in there in the center of this surface. And again, this function, z equals y squared minus x squared, is a surface. It looks like this. And there's x and y in the z direction. So three-dimensional, object. And in the center here is a saddle point, 0, 0, because you'll notice it's not a minimum because technically it goes down more, and it's not a maximum because it goes up more, so it's a saddle point. It's kind of slumped in there in the middle. So here's a saddle point. So we can conclude that this, in conclusion, our function that we were doing, question number 5, because, right, oops, too thin, because D equals negative 4, that's less than 0, we know the point. This is how you would write it on your test. And the point, you don't say A, B, you say negative 2, negative 3 is a saddle point. Saddle point. Okay? So that's the system that you want to use to go through these functions. I will go through it again briefly. Here we go. Ready? You have this function and it says find the relative maximum or minimum. The first thing you do is you find the derivative in terms of x. Then you find the derivative in terms of y. And then you set the derivative in terms of x equal to 0, y equal to 0, and you get this point, negative 2, negative 3. Okay? And then you find these second derivatives, zxx, zyy, zxy, and they will come down to these digits for these sorts of problems. And then when you have those, you find this d as in delta, and you take zxx times zyy minus zxy squared, you'll get some number, and then you compare that using your function here, and you try to figure out if z is greater than 0. You compare these things to figure out which situation you're dealing with. If d is less than 0, you have a saddle point, and then you make your conclusion. Okay, so that's how you do it. And I just wanted to leave you with this. Here is the picture of our function, and you can rotate this around. Ooh, and see, you can rotate it down too. Up and down. So these things are pretty cool. So, saddle points, functions, and this is what we're doing. We are looking for these maximum and minimum points. Check out this thing. There's this optical illusion. Woo, 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 woo. Cool. Okay. Let me know when you get stuck.